One other way rational functions occur in physical situations is through the idea of inverse variation or inverse proportionality. And so the definition of this is just that if two quantities vary inversely, specifically if y varies inversely as x, or y is inversely proportional to x, we'll write y is equal to kx. You could also say it's like x, y is equal to k if you don't want to write division. It's a little confusing that way, so I would recommend writing it as division, y is equal to k over x. And then k is just your constant proportionality. And then in certain instances, right, you might have an nth power of x appearing in there, so that just put the exponent on x and move on. Okay, so the exponent happens to come into play with this first example. So radiation machines, blah, 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 you can read all that there. But moral of the story is that I varies inversely. So when I see that as a mathematician, I write I equals k times whatever follows the square of the distance. So I is equal to k over d squared, square of the distance, k time or k divided by. Okay. So that's my equation. And then I don't know what k is, but I think that's what the next sentence is helping me to figure out. So at 2.5 meters, so if I put in 2.5 meters, so k over 2.5 squared, the radiation intensity is 80 those. I don't know how to say that. Okay, milliroentgens. I hope I said that right. Okay, but anyway, this gives me enough to figure out my equation. And so to solve this, I'd multiply both sides by 2.5 squared. 2.5 squared. Okay, so k is going to equal, with my handy dandy calculator here, 80 times 2.5 squared gives me 500. Okay, so in all, my equation is I is equal to 500 divided by distance square. Okay, so that's the equation I will be working with. To answer, oh, last part. So it says write a function that models I as a function of d. Okay, I did that, yay. And then use it to determine the intensity at a distance of 4 meters. Okay, so this is formally I as a function of distance. So then I could do I at 4 meters would be 500 divided by 4 squared. And I think I'm just going to leave that as 500 over 16, and that can probably reduce. Does it divide evenly? It does not, but if you want to or need to put it in decimal form, you get 31.25 milliroentgens. Yep. Somebody's going to teach me how to say this word. Milliroentgens. Yep, sure. We're going to go with that. Okay. Put it into Google and tell me how Google says it. There you go. Now, that was one example of inverse proportionality. Big idea, I is equal to k divided by whatever follows. Okay, so now the next one. You probably have ran into the ideal gas law before, right? Health sciences students do a lot of chemistry, right? So we're just going to make some simplifications, and the whole context is here. Not going to worry about that. What I care about is this paragraph here. Okay, so for simplicity, we're going to assume temperature is fixed. So this whole side is a constant. Okay, so it's like PV is equal to K. Oh, okay. And so we can say volume varies inversely as pressure. That's the phrase I was looking for. V is equal to K over P. All right. All those words, and we just needed the last sentence. Reading is a valuable skill. All right, part A. What is the domain and range of V of P? Okay, well, why don't you just, I mean, if we're thinking in a physical context, like pressure, right? So the domain is pressure and the range is volume. So like what makes sense for pressure and volume? Aren't they both just like 0 to infinity? Like you can't ever have a pressure of 0 on something because otherwise you don't have it. But then also it would just continue increasing to infinity. And in this case, you actually can't have a pressure of 0 because you divide by 0 and bad things happen, right? So there we go. And so if we want to now say that k is equal to 20, we would get the equation v is equal to, or the function rather, 20 over p. And so if we were to sketch it, let's see, if I put in, so let's say I'd have a vertical asymptote here at the P is equal to 0 line. Horizontal asymptote is also going to be at 0. Okay, I'm just doing a very, very quick sketch. And then I might need some points. So if I put in 1, I get 20, 20, positive. So 120. If I put in 2, I get 10. And then if I put in, there's 3, there's 4. If I put in 4, I get 5, right? So something like that. And so I get this sort of behavior going on. Okay. Very quick sketch, and you can fill in more details. And then where are the asymptotes? Okay, I included them in my sketch, but what do they mean in context? They just mean that if we think about the vertical asymptote, so VA at P is equal to 0, and we have HA at V is equal to 0. This just means like we can't ever have a pressure or volume of 0, right? Because otherwise that doesn't happen in our physical context, okay? So just like the last video, when we're in a certain scenario, we have to make sure that we're interpreting and thinking of what the asymptotes mean in context and whether they make sense or, how they could be useful in aiding or enhancing our understanding of that context. So went through this example kind of fast, but main point is here, when we're working with inverse variation or inverse proportionality, make sure to write it as y is equal to k over y is equal to k over x. So again, here y equals k divided by with inverse and then x. Okay. Same thing with inversely proportional.